In the last video, we saw that whatever AB you take strictly positive, this function x to the power a minus 1 into 1 minus x to the power b minus 1 has integral over 0 to 1 some real number, finite number. Now this quantity is of course a non-negative quantity when x lies between 0 to 1. So you have a non-negative function with finite integral. So it's only natural that if you divide by this, you take the function, divide it by its total integral, we shall get a density. And that's how we come to the beta distribution. It is defined like this. Say that x follows beta distribution with parameters a and b are strictly positive. If x has the density, this thing divided by its total integral when we are between 0 and 1, and otherwise we take it to be 0. So this is the beta distribution. Just notice one thing. If I interchange the role of a and b here, then the beta function remains unaltered, because just substitute 1 minus x for x, you will find that a and b swaps place. However, when we are talking about the beta distribution, these two things play distinct roles. So beta AB is different from the beta BA distribution. But beta AB is same as beta BA as the function. Just a little confusing terminology. Now, since the density has a power of x here, so if you want to compute any moment x to the power something, expectation of x or x square or x cube, that will be absorbed here to provide something which is again expressible in terms of the beta function. As an example, let's compute the expectation of x, which is a divided by a plus b. So the first parameter divided by the sum of the two parameters. Now the proof is pretty straightforward. Expected value of x is given by the usual integral. X times the density integrated from minus infinity to plus infinity. Now in our case the density is non-zero, only over 0 to 1. So it becomes integral from 0 to 1 x, this is the x, and here is my density x to the power a minus 1, 1 minus x to the power b minus 1. This beta ab in the denominator is constant, so comes out of the integral. Now this x, or any power of x for that matter, would get absorbed into this. That will produce x to the power a times this. Now in order to write it in the form of the beta integral, I will prefer to write it as x to the power something minus 1. So I will write it as x to the power a. Now I will write it as a plus 1 minus 1. Immediately I recognize this again as a beta function. Beta a plus 1. B remains as before, and downstairs I have the same beta AB. Now I shall use the result that beta can be expressed in terms of the gamma function. Here is a quick reminder of the result. So I will use this both upstairs and downstairs to get, this comes from beta a plus 1 comma b. Now I will do the same thing with beta AB in the denominator. So I get gamma a times gamma b in the denominator, and in the numerator gamma of a plus b. One cancellation is immediate. Now I shall use the property of gamma function, which is gamma of x plus 1 is x times gamma of x, and this holds for any positive x. So if I apply it here, I can see that this is a times gamma a, so there is another cancellation over here, and this gives me a, and similarly another cancellation over here, and this gives me a plus b. So together I get the result a divided by a plus b. That is exactly what I had to prove. You can easily understand that even if I work with expected value of x to the power something, essentially the same technique can be used. Now we shall see the different forms or different shapes of the density of beta distribution depending on the values of the parameter a and b. Now we need to plot it only over 0, 1. Remember, a and b are both positive, and since this is a constant, just a positive constant, we can forget about it when we are dealing with just the shape. If a and b are both strictly positive, in that case it looks something like this, because at 0 it is 0, at 1 it is 0, and whether it will bend like this or it will bend like this, that will depend on the values of a and b. If a is less than b, then it will behave like this, and if b is greater than b is less than a, then it will look like this, that is, it will come closer towards 1, and here it will come closer towards 0. If b is equal to a, it will be perfectly symmetric. If a and b are both equal to 1, then you can easily see that this is just a constant function, so it will be just the uniform 0, 1 distribution. If a is less than 1, of course it is greater than 0, then this end of the density will shoot up to infinity. What will happen to the other end? That depends on what is happening with b. If b is also less than 1, it will just shoot up to infinity at both ends. If it so happens that b is equal to 1, then it will hit some finite point here. And if it happens that b is greater than 1, then it will hit 0 here. And similarly, you can have just the other behavior. B is less than 1, so it is going up, but a is equal to 1, so it will hit at some finite non-zero height. If a is greater than 1, in that case, it will hit 0. So you see, the same family of beta distributions accommodates lots of different forms. So here is an exercise. If x has beta AB distribution, which means it has this density, find out the distribution of 1 minus x. Just by looking at it, you should be able to guess what it is, then prove it using either the Jacobian formula or you can use the CDF method, but the Jacobian method will be the easier.